In this video, we're going to look at the process of converting and then importing a conventional survey traverse file. In this case, we'll experiment with a FieldGenius file. So we can see in StarNet, I've started off a project, and we can look at a few important settings. It's a 3D project. We've used meters to collect it. I'm just using a local coordinate system. Now, I'll need to run a separate program, which is the star FieldGenius converter in this case. So I'll open it up. First step is you select your input file. So I'll browse to it, and there's the raw file that I've got. And you also have to specify where you want to output the file. So I'm going to browse, and in this case I'm going up a level because I want to store it in the same location that I've got this project stored. Now, something that I would like the project to do is pay special attention to redundant side shots so that they'll be shown as M lines. So everywhere where there is a redundant side shot, I want it to write an M line instead of an SS line. M lines will be considered part of the network. I'm not going to select any other special options. I'm just going to go straight to import. Okay, so now it tells me that the conversion is complete, and I can say OK. If there had been any errors, it would have been a good idea to go to the View Log button, because this might tell me what line number there was a problem. So I'm finished with Star FieldGenius, so I can close it. So right now, all I've got is a DAT file, and in this case I've made myself a couple of notes so I can remember the steps. And now I have to bring that data into the project. So I'll go to the Add File button here, and I'm going to browse to that DAT file that I just created, and I'll open it. So now it's part of the project, but I can't see its contents yet. I just double click on the icon. Here's the contents of the file. So right now we can see that in this case we had stored the point 1 with those coordinates. We did an initial backsite from 1 to 2, and then we've got a series of setups and angles that were measured on the network. Now you'll notice how StarNet has automatically commented out the first store point that it found and the first backsite direction that it found. It wants to leave it up to the user as to whether or not they want to use those values or if they want to input their own values. In this case, I'm perfectly happy with those. So I'll just take the pound sign out from the C record, and I'll take the pound sign out from the B record. Now at this point, we've got all the information we need to calculate a network, and in fact I can do the data check function here just to have a look if it's going to work. But at this point we can't adjust the network because we don't have any fixed points or fixed directions. For a conventional network, you need to have at least 2 fixed points or 1 fixed point and 1 fixed direction. So I've got what I need to make a fixed point. So I'll use 3 exclamation marks to tell it that I want to fix the northing, the easting, and the elevation from this entry. And then down here, I'm going to tell it that I want to fix the direction of 1 to 2 to due north in this case. So I'll put an exclamation mark there. Now we can run the data check, and here I'll say yes to save those edits that I've just made. Data check is happy, and we can see from the network plot I can visually confirm that it does look the way I'm expecting. So here I can go and I can do the adjustment. Let me open up the network data check window, and then I'll run the adjustment. Okay, so here we can see we've got our network adjusted. We can see our error ellipses, so we can see where the strengths and weaknesses of the network are. And we can also see that we've got a chi-square test. And in a perfect world, this chi-square test would come out with a value of 1 in each case here. And that tells us that the error level that we've told the program to expect and the error level that was calculated balance or match each other very nicely. In this case, we've actually failed the chi-square test on the lower bound, and so that tells us that our actual measured results were better than we told it to expect. in the project settings. Now, more often what will happen is the initial run, the chi-square test fails, and that tells us that there may be some outlying data, data that doesn't match too well with the bulk of the project, or it might tell us that there are some blunders in the project. And so the operator's job would be go and find those outliers and those blunders and either correct them or delete them from the project. But I have a happier problem here where I have to find out why it's exceeding on the lower bound. And I think that's probably by going into my instrument settings here. And right now I've just got the default settings for what kind of an instrument I'm using. I've told the program that I have a total station capable of 4-second angles. My assigned directions are reliable to 3 seconds. Down here we can see that there is a setup error of 1 centimeter in all 3 areas. And the reality has been that we've actually done better than that. So why don't I change it? I'll just fiddle with the settings a little bit. I'll change my angle to a 2-second instrument, and it's probably more realistic for my setup error to be something more like 5 millimeters instead of 1 centimeter. And then let's run the adjustment again. And now, so we've still exceeded the lower bound, but you can actually see that we're closer to it, because what we're doing is we're comparing this number here, and we want this number to fall between that 0.792 and 1.208 value. So I would just need to go back into the instrument settings and adjust things until I actually had something that was acceptable. And at that point, you can go into your report, you can spit that out, and you've got a result that you can be confident of.